Good morning, everyone. Thank you for being here. I'm going to go ahead and get started. People may filter in as I get going, but first I wanted to take a moment, thank you guys all for being here, but also thank SME and thank Roger, Stephen for your efforts the past 3 days. So thank you, gentlemen. If you see me staring off like a lost dog or just kind of blankly looking into the ether, it's probably because of all these machinery going. I'm not used to it. It's quite an interesting place to have a presentation in. But nonetheless, I was going to talk today about, I have for the Douglas Adams fans in the room, A Hitchhiker's Guide to Metal Additive Manufacturing, the haves and have-nots to evaluate additive-made parts. It's just to kind of equip you with things that we see being a machine manufacturer of powder bed fusion additive manufacturing systems, and really just some things to consider as you might approach this technology. So diving in, just to establish some credibility or some baseline of who the heck is this guy and who does he work for. SLM Solutions is a powder, like I mentioned, a powder bed additive manufacturing system provider. We're based here in North America in Wixom, Michigan, and globally headquartered in Lübeck, Germany, where we have about 330 employees worldwide. We should be about 100 million in revenue this year. Our focus is high throughput production class technology. So what we're looking to do is help customers advance this technology for production. And how we do that is through multiple lasers in scaling these machines, as well as through open systems where you're allowed to use third-party powder providers, as well as we have open parameters for running these said materials. Also, safety is a key focus for us, where we have closed loop systems where outside of the powder getting into the machine, it's a closed loop system where there's no operator exposure to open powder. So that's kind of in a nutshell who we are. The history of the company actually dates back to the late 19th century, but really when it comes to 3D printing and rapid prototyping, that came about in the 70s, and the actual invention of this technology was developed by our Chief Innovation Officer, Dr. Dieter Schwartz, in the mid-90s. Really, that took us into the, hi gentlemen, welcome. That took us into the early 2000s, where we really put in the R&D effort of this technology, and then commercialized it with the introduction of the 125 and 280 in 2011, and the dual and quad laser 500 in 2013. Where are things headed? Obviously, customers want bigger, more speed, bigger build sizes. In that, as it relates to powder bed fusion, gas flow is a real key consideration in how you do that. Being able to remove that soot and smoke in building parts. So that makes things a challenge, but we're working on that very hard. As well as what you also see is a lot of software peripherals or means to verify process and quality as it relates to making these parts. So, hi gentlemen, come on in. About me, I'm regional manager for the Northeast, covering everywhere from Virginia on the way through Pennsylvania, all up into Canada and all points in between. Been in technology sales for the better part of 15 years, and of course, I have a liberal arts degree, which makes me completely qualified to stand on stage here and look at you folks in the eyeball, because for those of you who have built parts can attest, you sometimes need a little philosophy and religion in getting things done. Diving into the meat and potatoes of the presentation. So I guess in the Hitchhiker, as an ode to the Hitchhiker's Guide to the Galaxy, you got these little planetary entities here. Applications in red and is the biggest, because that's the key driver you want to start with in looking at additive-made parts, metal additive-made parts. We see a couple different approaches as it relates to the application, but for most folks it's weight optimization, product or improved performance, as well as maybe a part consolidation that they're looking at, a variety of factors that go into considering metal additive for the production of that part. Beyond just the application, we also have lots happening in the material side. So if 50% of the product development process is, what are we going to make? The other half is how are we going to make it? So there's a lot going on the powder side, the material side that I'll touch on here in a couple slides. But that's also another key consideration, because maybe with the certain materials that you're producing with conventional manufacturing, Now, that may not translate to metal additive manufacturing, so that's a key consideration you also want to make. Further, you then have the machines. So again, SLM Solutions does powder bed fusion. You may also hear it referred to as DMLS. Lots of different laser cusing, a variety of different naming conventions that really harken back to powder bed fusion. But there's also direct energy deposition. There's electron beam melting. There's various different technologies as it relates to metal AM. And again, it all focuses back at the application. So as it relates to the overall market, the relevance of powder bed fusion accounts for about 77% of metal AM systems sold. Reason being, it actually has slower deposition than some of the other various technologies I just mentioned, but the feature quality is typically the highest in powder bed fusion. So I think that's why a lot of customers gravitate towards it. Again, each different technology has their own benefit or ultimately value. If I get that little piece up there, of why the heck you'd even buy this stuff. So again, driving the value or trying to find the business benefit to why would I introduce this to my organization, we would start with the application, then go to the material, then go to the machine in helping you to advance that. Now for us, as I mentioned, we're focused on high throughput production class systems, and how you get there really is through the sprinkling in process control and best practices. So those that have experience and expertise as it relates to developing parameters, working with these various materials, being able to drive that application, that's really where the secret sauce lies as it relates to metal additive and folks taking this technology, for production. So as it relates to the applications, just to give folks a little more detail as to what I mean there, again, in the Hitchhiker Guide to the Galaxy, don't panic. There's a direct and indirect approach to considering additive-made parts. I'll start at the bottom. Most folks come to us and they say, hey, we have a legacy part here that we would like to do with metal additive. And that's great. You got to start somewhere, right? And so that's a completely logical place to evaluate this technology. However, there's also less ROI sometimes there and less value, because you guys know how to squeeze blood out of a tournament. You guys are great at making parts. Therefore, it's really hard sometimes, if you're thinking, I'm just going to save time and money in making this part via metal additive manufacturing, that may not be in fact the case. So another approach is to look at a opportunity or a unique way to leverage this technology in a completely from scratch way, where you're able to have a direct approach where you consider design for additive manufacturing and are able really to, again, look for weight optimization, maybe product performance, do a unique material that's never been done before. Maybe if something was done on aluminum, you're going to look at titanium. Again, something that would allow you to do something unique and different. That's for us where we see more value, more ROI in adding this technology. So we can talk more about this for those, and forgive the shameless plug, but we are in booth 1269 here at the show. So we can talk more about the direct and indirect approach you can take to the application. But these are, again, just some things we've seen, or it's been our experience working with customers on adding this equipment. Why would you do it? Again, technically, it's going to reduce constraints on manufacturability, allow you to optimize the product. From a business standpoint, this gives you the possibility to open into new markets or penetrate existing markets more deeply. Certainly, there are plenty of instances where faster, better, cheaper, and more innovative is the outcome of this, but it's not always the case. So I just want to be realistic that not every scenario does additive make sense. So where we see folks adding this technology is both in critical process as well as in critical path. Again, for us, and where we're focused is on those wanting to take a part on a critical path, but we also have those that need to start somewhere in just gathering IP, learning about this technology through critical process. So while we certainly do have folks doing materials development work with our equipment, being able to find that fit find those group of parts that might make sense for additive manufacturing. We do have folks that are currently in production in various industries of aerospace, energy, automotive, tooling, medical, and dental right now. So, and probably in that order, to be honest. Again, aerospace is looking at weight reduction. You know, we all want to pay less for plane tickets, so they're looking anywhere they can to reduce weight in their fleet. In energy, you know, you guys have seen maybe a fuel nozzle from a very large OEM in the world. You know, that was took a heck of a lot of R&D effort to develop it. That was a $5,000 part that they're now selling for $50,000. But we're seeing a lot of very unique things as it relates to conformal cooling and, you know, a boring part on the outside that has a lot of interesting stuff going on the inside that you could never make via conventional means. So a lot of risk and reward that as it relates to the various use cases that we see, both in the, I'll say, research and development side of things, as well as then and also in production. A simple sample, and this has not actually gone into production, but this came from the Additive Manufacturing magazine in March of this year. This is a turbine engine that a group of engineers were asked to repurpose and redesign. What could metal additive do with this turbine engine? It was obviously, you know, 50% of it was redesigned. They consolidated 900 parts down to 16, ultimately receiving a 60% cost reduction in this engine. Now, that all sounds lovely. Obviously, you guys can certainly take in those numbers and see there's a lot of inherent value in ROI here, but you know, it really is unique per the different part that you're considering and per the application. So one exciting thing I know for a lot of OEMs, I will say this here. We have a lot of OEMs adopting this technology, and that's great because they need to get their arms around how to best leverage it. And we also see a lot of startup folks that are just, you know, trying to turn a quick buck. What we need is a lot of folks like you who know how to build parts adopting this technology, because that's really where the OEMs want to provide you that work so that you can do this in production. And so that's where for us, where we're really focused on hoping folks like yourselves who build parts every day start to adopt this technology and really hone it and make it your own. So more to part selection. When it comes to designing from scratch, taking that direct approach I've mentioned, you know, consider the geometry. Is it complex? Is it a low quantity? Is it a unique material? Also consider the supports. You know, supports actually remove some of the thermal energy that the part sees in the powder bed process. It also helps to keep it anchored to the substrate. So that's a key consideration. If you can't remove those supports, especially when it relates to like conformal cooling applications, things of that nature, that can become very difficult. On our manufacturability side, though, it does reduce restrictions that you might currently see through conventional means, as well as also allows you to do some of those swoopy shapes, those crazy organic parts that you know, you've seen designers design the world over, and you're like, that's great, but nobody could ever make this. Well, maybe now you can. So additionally, when it comes to selecting existing geometry, I would say definitely look at geometric complexity. You know, a simple prismatic part is probably not the best use case. If you're just looking at it thinking, well, I can, you know, this takes us a long time to build, and I can print it. I can print it or manufacture this additively, and save a lot of time and money. It may not work out that way. It could, but I just warn you that it may not work out that way. There is, though, the ability to save from tooling and manufacturing costs as well. We do have folks using it on the manufacturing floor currently as it relates to jigs, fixtures, work holdings, various means internal to their process. This is much of the same, but you can kind of see the breakdown. High complexity, organic shapes, low quantity. Those are target parts where we say those are good candidates to consider metal additive manufacturing. Digital, this one's interesting. A lot of folks really are interested in this one, where they're able to, especially your governments, the military, things of that folk, you know, they got aircraft all over the world and they need parts now, and they can't wait 9 months for a part to arrive. That's certainly interesting, and we have that happening, but there's a lot of development that needs to take place for that to really be pulled off well. So As it relates to materials, you can plug and play these materials, these powders. When I say plug and play, the parameter sets are all available from any of the major metal additive manufacturing providers for any of the materials that you see on the screen there. You can, and they, we provide powder. I'm sure all those as well in the space have powder available that you can buy and run this stuff today, and create beautiful parts, frankly. Stuff that you guys would be very impressed with. A secondary option, for us is you're able to, like I said, we have an open architecture. You're able to use third-party powders from the various suppliers in the world. These guys got, lots of resource that is being poured into developing additional materials for additive. The real criteria we look for is it's weldable. The particle size is typically particle size for us. Like right now on the show floor here, we're running 20 to 30 micron beds of powder, a bed of powder, and it's typically anywhere from 10 microns to 75 microns that you would see on the powder bed. It needs to be good spherical size as well as have good flowability, but if it meets those criteria and it can be atomized into powder form, you can run it. Now we may have to help develop parameters for that material, but you can run it. One unique thing about us is we do have a material development module, which allows you to actually hone in those parameters, those process parameters that you would actually build that part. You can see this image here on the screen where I have all these cups. Instead of this taking 25 separate builds for each one of these cups to evaluate or optimize those parameters for that part, you can actually iterate or make unique each one of those cups with a different set of parameters to actually optimize that build. Now, why do you want to do this? If you're taking a part to production, there may be porosity or surface roughness, some type of part quality that you're looking to achieve in building that part, and having this ability will allow you that flexibility in doing so. So, again, fast identification of optimal parameter sets and keeping this IP in-house. The critical controls and parameters as it relates to powder bed fusion, you have the laser power, so the actual thermal energy that's hitting the powder bed. You also have the scan velocity, how fast the galvos are bouncing that laser across the powder bed floor. You then have the track distance between of where the laser is actually hitting the powder bed, as well as then the layer thickness. Again, that typically for us 20 to 30 microns is what we have as it relates to the layer thickness of a bed of powder. You can see the images here, but one big piece to consider if you are saying, you know what, we've identified the application, we have a part that we think is a good candidate for additive manufacturing, we know what material we want to do, we think this makes a lot of sense. When you start to go shopping, one real key piece is the gas flow. As I mentioned, everybody wants bigger machines, faster machines and all of that, but a real key consideration all that is gas flow. Being able to remove the soot and smoke. These machines are under inert gas environment, and you can see this took some learning on our part. So that's where you see the traditional, the images in red here, as it relates to porosity and surface roughness of the parts. We got some variance as it related to the build plate in part quality from one side of the plate to the other. Optimizing the gas flow, which took a lot of focus in R&D development, allow us to get it where we now have a flow that we know we're achieving 99.5% density in parts, no porosity, great surface roughness, part quality is very high. Again, gas flow is a key consideration, all that. It actually took us, you can see here in the image, this is a perforated wall, which has it's porous, so it allows more airflow, as well as then we have air blades to keep the lenses clean, as well as an air blade on the bottom right above the powder bed. So that's allowed us or helped us through, again, lots of computational fluid dynamic analysis and those things to optimize the gas flow in the machine, which does ultimately affect part quality. Materials aren't irrelevant if quality isn't there. So we have some various tools on board our systems, others have them as well, that allow you to understand powder delivery. For us, We have a layer control system that basically it'll take a image, a shot of the powder bed of the laid bed of powder, and if there was an issue, the machine knows to go and try and make lay another bed of powder. If it has a second issue in doing so, it will actually stop the machine. That's an important piece. You need to have a good, even bed of powder if you're going to hit it with a laser, with a high-powered laser. Also, though, we actually have tools, and we have this on display here at the show, which we're excited about. This was introduced this year. We have means to monitor the laser power. As you're doing hatching and various things, contour and hatching, you'll see fluctuations in the laser power. You can actually see this real time on our machines, and why is that important? If you had a part defect or maybe a part issue or something happened in the build process that didn't go right, that could give you a reference point as to tell you maybe something's happening here. Maybe there's something going on with the laser that I need to take into consideration. Additionally, in a similar way, we also have the energy to powder reaction, so with the melt pool. Basically what we're doing is we're taking a refraction of the melt pool, the thermal emission of the melt pool, collecting that data. Again, what do folks are doing with that right now? They're able to actually use that as a reference point in understanding if a part issue took place, how can they correct it? It gives them just, instead of just looking for a needle in the haystack, they have something to hone in on. I know for us, SLM, we have an applications team. That's what they do all day. And a lot of times, there's lots of characteristics, lots of variables at play when it comes to metal additive that need to be taken into consideration. So instead of just looking at all of it and trying your best, this gives them some place to start in honing in on what the problem might be. Additionally, I mentioned to you, actual tools we have, but I'll say this at this point: this is not a lone wolf industry. This is not, hey, we're going to buy a machine and good luck to you. We'll talk to you sometime down the road. It's moving so fast. It's such an emerging technology that you really need support and assistance. And the hard part about that, the challenge is for those that have made that investment, they want to keep that IP to themselves because they've spent a lot of time and resource in developing it. So that's really where who you partner with becomes a key consideration. The way we purpose it is we have an applications team who is the machine on and working great. We got a staff metallurgist on hand. We have folks that are skilled, very senior people in parameter development, a variety of folks to help on the various things that you might encounter, as well as on the flip side, if the machine's not working, we have a whole team of field service folks to help with repair work, preventative maintenance, all of that. So just a little bit about materials. For those of you who are unfamiliar, if this is completely new and I'm like, I don't even know what a powder bed, why does this guy keep saying powder bed fusion? This is a digital image of the actual process. If you're sitting out there saying, man, that stuff sounds really hard, I mean, there's a lot of stuff he's putting out there. If you can see here, this is an actual high resolution camera that the folks at Lawrence Livermore National Laboratory put together to this is an actual laser hitting the powder bed. And as you can see, we're trying to control chaos. This is a crazy process. That's why things like gas flow become so important, is because this is not easy, right? That is why scaling these machines is not easy. And I know everybody's going bigger, but that needs to be done so in a calculated and thoughtful manner. So, again, just to this is the review slide, right? They'll tell us to do that with doing these types of presentations. So, obviously, we're all looking for value and ROI, and why the heck would I ever buy that stuff? Again, for us, it's really looking at applications. Is there new, improved markets that we might be able to enter in? Is there an existing market that we might be able to penetrate more deeply? Is there reduced time and cost overall? There is certainly tons of parts that we've encountered where they're just cumbersome to produce. And metal additive has allowed, especially with those organic shapes or low quantity items, allowed us to have metal additive be a viable means in those situations. Additionally, you have the materials. So I showed you those materials that we have offered today. Again, every day there seems to be new powder. The powder providers are offering new materials all the time. You know, it will take time for us to develop parameters for some of those, but there is a lot happening here, but we may not have the material that you need. And so just be mindful of that as you go exploring metal additive. Additionally, if applications are driven by materials, materials are enable the machine. Look for accuracy, surface finish, precision, and metal integrity. I think those are all key items in how the machine can run that material and produce that part. So for us, you know, we take, if you're really serious and thinking about doing this, it makes sense for a part you've identified. We go through a full benchmark process where we actually print a part for you. You're able to evaluate it. We do metallography on that with some test coupons, tensile bars, just to see, do we have something that might be a viable candidate to really add this technology and take it to production. So if enabling the technology, how big, how fast? So, you know, like, this is nothing new. We have a small, medium, and large. What's exciting here as you get into medium and large is we get into the multi-lasers, where in our SML 280, we can do dual lasers, so you can have an overlap zone. And obviously, the way to scale these machines is to add more lasers. It's simply that, you know, if you want 99.5% dense parts, the only way to scale this stuff is to add more lasers. Again, in doing that, it becomes a challenge in removing soot and smoke, or the gas flow becomes crucially important. But our 500 machine that you see here, this is the folks that have added it, that's specifically focused on production. So most folks that add it, it's typically a part, a material, and it's going to stay that way from now until the cows come home. So if you're looking for kind of a catch-all, that's kind of our 280 here, where for us, it allows you to do some of that material development work, some of that critical path stuff that I was talking about, critical process stuff that I was talking about, and then ultimately you could purpose that. We do have folks with production, doing production parts, or going through critical path parts with the 280. So this is our lineup. Common to all the systems is we do offer, it's top bed, so we use gravity to our advantage. That allows us to be, from a safety standpoint, have it be a closed loop system. There's some other key benefits as well, like we have a bidirectional recoater. So the recoating of the powder is a key consideration in the various layers that you would take to build the part. Each layer, it takes about 8 seconds for the recoater to lay a bed of powder. So if you're able to do it forwards and backwards, that saves time. It also helps with the dosing bins and the dosing strategy that you would have for this technology. Also, we have standardized lasers and optics in all the machines. Why do I care? Why is this important? Well, as you scale, let's say you wanted to do some material development work on maybe our small machine, where it has a smaller build size and you're able to just do that material development work. That actually scales to our largest production machine because the lasers and the optics are all the same. So your homework's essentially most of the way done for you. So we, again, open parameter sets for user customization. We can give you material, you can get a machine, get some powder, and get a parameter, and we could make parts that day. And that would get you probably 80% of the way there, or 85%. But that other 15 to 20% is where you guys want to kick the training wheels off and really make the thing sing. And so having that ability to get into the parameters and really hone in on those things, that's where the upside is in having that open flexibility. Again, we have open through-door access where you're able to access the chamber outside the machine. Again, I've already gone through the closed-loop powder handling, but we do use a soft recoater. It's a topic of discussion in many is hard versus soft recoaters. If you have a lattice structure, something really fine-featured, a soft recoater, we found that won't actually nick your geometry or compromise your geometry in having a build. So we've been using a soft recoater for a number of years, and that's been very successful for all our customers. In fact, most all our customers use a soft recoater, though we do have a hard recoater available. Again, we just found that the elastometric recoater is ideal. Efficiency optimized for low gas consumption. Our machines sip argon at about 4 milliliters per hour. Some others that may be more. This can be a healthy consideration as you consider the business side of the equation in your gas flow consumption. I mean, if you're running argon, That could mean as much as $100,000 a year. So something worth considering as you evaluate this technology. Finally, as it relates again to part quality, I mentioned to you that we have the laser control system. I'll start at the bottom again, forgive me. This verifies the integrity of each powder recoat prior to scan. Again, it will self-correct. The machine is intuitive enough to understand if it had laid a bad bed of powder. It's just doing a grayscale overlay and seeing if there were issues in the recoating. That's available on all systems, as well as the process sensor monitoring. So verify consistent process conditions and it records this information every 2 to 3 seconds. So your oxygen levels, your optical bench, how it's performing. All these things are actually recorded every 2 to 3 seconds, just to make sure that there's no anomalies or nothing out of ordinary as it relates to the build. I'll mention these again. We do have what's called laser power monitoring that actually takes a beam split or a refraction of the laser and collects that data to verify what was actual to the parameters that you asked the machine to run. They are independent on each laser. You can kind of see the diagram here. I know it's a little hard to probably read, but you can see how it's got a beam splitter and it's splitting off to collect that data. Additionally, on the same vein, we have melt pool monitoring. That is taking a thermal emission of the melt pool to collect that data. Why should I care? What the plan would be for us to synchronize and aggregate this information to have the machine do more self-correction. This is a ton of data, guys, that we're collecting. And so we need to hone that a little bit where we're able to actually feed that back to the machine and allow it to do some self-correction and be more intuitive. So finally, this is the sales slide or the pitch slide. Forgive me. I know I got a captive audience and you guys are sitting here. You know, for us, we like to deal in competency-based facts. More parts produced for each dollar spent on metal AM. We do this through top-fed bidirectional recoating, multi-laser scanning. So again, that high throughput production class focus that we're looking at. We try to give folks, you know, it's your machine, do with it what you will. We want to give folks flexibility and having having this open philosophy of powder and parameter options that best suit the part application and development work that might be done. Finally, it's got closed loop, you know, safety is a key criteria. I can't tell you how often we've been working with customers where there's lots of fun and exciting conversations around engineering and manufacturing to then have the safety engineer come in and say, wait, what are you talking about? Aluminum, titanium, those are reactive metals. Wait. There's a lot of science and effort and training that we've developed to allow those folks to have their needs met. I will say, for us at SLM, we have a staff PE in-house just to help with those safety folks, where all his job is to help with getting with the surrounding infrastructure as it relates to this equipment. So if you have curiosities to that, again, I would encourage you to come visit us down at 1269 to discuss that more. I'll stop with the selling. Again, I'll make this brief. Great candidates for this technology is it's a completely boring part on the outside, but there's a lot of interesting stuff going on the inside. Unfortunately, I had never heard of that company. It is a European company, but a lot of our customers, we can't talk about what they're doing with this technology, but this was one that was kind enough to allow us to talk about it. Using our 280 twin, this is an Inconel part. You know, they were able to integrate temperature channel without support structure. That was a big key piece in all this, where they were able to have a minimum wall thickness for fast reaction time. Again, just a boring part on the outside that has a lot of interesting stuff going on the inside. On the organic shape creation side, you know, with the topology optimization softwares that exist today, you can make some really ornate, incredible organic parts. This is an actuation mechanism, and again, why would you do this? It reduced the weight, it allowed for less drag noise. There are brackets right now on airplanes that we all fly on, and there will be more of that as time moves on. A lot of cool stuff going on this end, as well as where this software, the software peripherals that I mentioned are being developed to help with this organic shape creation. finally, this is, everything you just showed me was pretty small. This used to be a cast part that a customer of ours over in Germany have a factory floor with 20 of these machines. This was done on our biggest machine, our Quad 500, but this is a huge part, and they were able to reduce weight by 30%. Finally, we do have scenarios where this part of the part is made conventionally, and then the rest we actually added the part to the powder bed or inside the SLM system, and then added features to a part. We don't see this a lot. There's some complexity to this, but it can be done. That's the whole point, is you can have, I will say this, metal additive manufacturing exists with all of this stuff. So they are in harmony. A lot of folks think, I'll have metal additive and it'll be separate from the conventional machining and conventional manufacturing that go on today. That's not true. The folks that are having success with this today, it is a happy harmony going on between the metal additive work they're doing as well as then their internal conventional manufacturing methods. So finally, that's all I had for you guys today. I hope I equipped you guys with a few ideas and thoughts as it relates to this technology. I'd be happy to answer any questions should you have them. Oh, he's got a microphone if you wouldn't mind.
I have a couple of questions. You listed a bunch of materials for additive manufacturing, but it seems zinc missing. Zinc is, kind of
zinc.
Material.
Yeah.
Why
It's a great
is there
question.
any future for zinc?
I don't know. I guess I would encourage you, since you're interested, to come down and visit with us. I have our staff metallurgist here today, Dr. Grills. I don't know why zinc. We've had various ones. Copper is a big one folks talk about because of its conductivity. It's electrical conductivity. Sometimes with the optics, I will say this. Sometimes with particular materials, what makes things difficult is their microstructure, their inherent material properties, as well as then sometimes even the refraction of light. I can say with copper, which I know is not zinc. The actual, because it's a reflective material, that bounces back into the optical bench, and that becomes an issue. So that needs to be worked through. I can't speak to zinc specifically, but I'm sure it's been brought up by someone else, and so I'd encourage you maybe to come by the booth and talk to us about it. So great question, thank you. Anybody else?
In quality inspection, is there any other processing required after it comes out of the machine, after the part is made?
Post-processing?
Yeah, in terms of material finish
or
finishing the part?
Yeah. So, great question. There is typically post-processing that takes place with the parts. May it be getting a better surface roughness. It is a layering process, so sometimes you may see a certain surface roughness as it relates to the part. We do have folks where they're doing some post-machining, they're either doing some peening. We do have folks, especially when it relates to like aluminum, titanium, doing some heat treating or hipping of that part to get certain properties or just get any last remaining, if any porosity did take place, it would address that. So sometimes they do that just to confirm that they have a fully dense part. Additionally, on the quality side, often what we'll do is we'll actually print test coupons and tensile bars that we'll send out for metallography just to confirm that the build was actually sound. You got a fully dense part that achieved the material properties that you were looking for. So that typically happens with every build, where we'll send it out for metallography, where those folks have the equipment to do that. We don't have metallography in-house. There's been talk of it, but there's folks that do it every day and they do it really well. So that's where we send out for where they have the CT equipment and all of that to do that work. So both of those things typically happen after every job. Again, and that's where the post-processing piece is where all of this really interplays great with metal additive. So great question. Anybody else? No? Thank you, folks. Appreciate it. Have a great day.